Now, something that comes up a lot in physics is interference, whether we're talking about the interference of sound waves like you'd use in a noise-canceling headset, or interference in the case of a laser, like constructive interference, where you're amplifying light by having lots and lots of photons of the same frequency. Interference comes up quite a bit. And interference is just saying that if you've got two waves and you mix them together, you're basically adding the amplitudes of those waves at given spaces and times. So imagine if you've got two waves that are propagating like this. If they have exactly the same wavelength and exactly the same frequency and exactly the same phase, so in other words, their k is the same, their omega is the same, and their phase is the same, and their amplitude is the same, then we would call that constructive interference. So we'd add those together, and you would wind up getting a wave that's twice as big. Okay, so those are adding those together. That's for constructive interference. And if you offset one of them by half a wavelength, so if we were to take that original wave like this, and instead, it's got everything stays the same k, same omega, but we give it a different phase. So we change the phase so it's off by half a cycle. So the phase is shifted by pi. That would mean that where there was a crest, we'd have a trough. And where there was a trough, we would have a crest. Trough, crest, right? And if we added those together, you would basically get a line, and that's destructive interference. So this is something that would happen in, say, a laser, where we're trying to amplify the light. This is something that would happen in like noise-canceling headsets, where we're trying to dampen down the sound. Now, there's a special type of interference when you have two traveling waves that move against each other. So if you have waves that have the same, again, same k, same omega, even the same phase, but one of them's moving to the right and one of them's moving to the left. So we have a wave that looks like this, and we have the exact same wave that has the exact same properties. The only difference is this wave is moving that way and this wave is moving that way. If you add these two waves together, they are going to alternately constructively and destructively interfere as they pass each other. So sometimes they'll be constructively interfering, sometimes they'll be destructively interfering, or some combination between. And what you wind up with is something known as a standing wave. And a standing wave is going to be something that in space is going to, if I make sure this has the same frequency, is going to look like the original waves, but later it's going to look like this. And later it's going to look like this. So it's basically going to, look like that, and then at some later time look flat, and then at some later time be the opposite, and it'll just oscillate back and forth like that. And you wind up with a wave that is oscillating back and forth in what we call a standing wave. And one of the best examples of a standing wave is the wave on a string. So you have something where you've got a node at two ends, where we have connected this to the ukulele here, and if I pluck this, one wave's going to travel up that way and one's going to go that way, but then they're going to reflect off of these points and go back and forth, and they're going to oscillate, traveling back and forth on this, and that sets up a standing wave on the string that oscillates at a particular pitch. And because of the way the waves are set up, you can only have pitches at particular frequencies given the size of the length of string that the standing wave is existing on, and the tension of the string. And that's why you get different tones when you play the ukulele.